Welcome to The Explainer. Today, we're diving headfirst into the fascinating world of geographical reasoning. We're going to look at a really high-stakes detective puzzle, figuring out exactly where in the world a single photograph was taken. It's the ultimate test of observation, and, as we'll see, it's actually become a profound battleground for comparing human cognition against artificial intelligence.
Okay, let's dive right into this. I want you to imagine a scenario. You're instantly dropped onto a totally random road anywhere on Earth. All you have are the visual clues around you. The dirt, the trees, the lines painted on the road. Could you figure out where you are? Well, for top players of the online game GeoGuessr, the answer is a resounding yes. But how they do it, and how machines attempt to mimic them, reveals something absolutely incredible about how we process the visual world.
Now, you might be wondering, do human experts just memorize the entire globe? Actually, scratch that. Google Street View covers over 10 million miles of road across 110 countries. Brute force memorization of that kind of data is literally impossible for a human. Instead, experts rely on a very specific, almost magical mantra. Pattern recognition scales, memorization doesn't. They learn a fixed checklist of visual patterns.
So, human experts use what's called a coarse-to-find reasoning chain. It's basically an active elimination game. You aren't just making a wild guess, you're systematically filtering. The moment you notice which side of the road cars are driving on, boom, you've just cut the map of the world in half. From there, you look for clues to narrow it down to the country, then the region, and finally the exact city.
To pull off this filtering, humans rely on a checklist of specific geographic scene attributes. They're looking at the language on a distant sign, the specific shape of a license plate, or even the design of roadside bollards. They even look at things you and I would completely ignore. These meta-clues, like the generation of the Google Street View camera itself, which actually leaves unique digital footprints on the photograph.
Now, what's really interesting is how hyper-specific these meta-clues can get. If a human expert notices very low quality and specific compression artifacts, they instantly recognize it as a Gen 1 Street View camera. And because Google only ever used that specific camera in the US, Australia, and New Zealand, the expert has immediately eliminated 107 other countries from their list. That is a real game changer.
And the physical infrastructure is just as revealing. Take a tiny detail like a traffic bollard. An expert knows for sure that a short bollard with a vertical reflector and a black cap on top is typically only found in Austria and former Yugoslav countries. That tiny piece of plastic acts as a massive geographic filter. It's a highly structured logical deduction.
Section 1. Can AI play the game? Peeking into the machine's brain.
So, the crucial takeaway so far is that humans use logic, context, and that coarse-to-find reasoning. To find out if a machine can play the same game, researchers feed a convolutional neural network, an AI trained on millions of images, a sample from Budapest, Hungary. A human expert would immediately look at the foliage or the train tracks, but what does the AI actually focus on to make its prediction? To figure that out, researchers use a tool called a LIME explainer, which basically acts like an X-ray for the AI's decision-making process. And the results are absolutely mind-blowing. The AI confidently predicted it was Budapest, but its decision was based heavily on a very specific blotch in the clouds. It completely ignored the tracks, the buildings, the whole shebang.
And it gets even weirder. When running another analysis on the exact same location, the machine hilariously fixates its heaviest weight on the front of the Google Street View car in the bottom corner rather than, the actual Hungarian environment.
So, what does this all mean? Well, while the AI might get the answer right, its reasoning is entirely alien to us. Early AI models succeed at geolocalization through brute force pattern matching of seemingly irrelevant pixels like specific road textures or sky patterns rather than structured human logic. It's just finding statistical correlations in the pixels, not actually understanding the physical world.
Moving on to Section 2, where machine learning stumbles, the context problem.
And this brilliantly illustrates the issue. Consider the actual Eiffel Tower in Paris, alongside replicas built in New York and hangs out China. A human instantly looks at the surrounding context, the cars, the nearby buildings, the layout of the park, to tell them apart easily. But the AI model confidently predicts Paris, France for all three. It sees the shape of the Eiffel Tower and suffers from tunnel vision, missing what researchers call axiomatic irrelevance, basically the obvious logical clues that rule out a location entirely. When we contrast the two, the difference is stark. A human expert provides an auditable, structured reasoning chain based on fine-grained visual details.
Modern vision language models, on the other hand, often confidently hallucinate their reasoning. They might guess the correct country based on some hidden pixel pattern, but when asked to explain why, they'll simply invent a rationalization out of thin air that sounds good but isn't actually supported by the real visual details.
Which brings us to Section 3, Teaching AI Human Reasoning, Bridging the Gap.
So how do we force AI to stop pattern matching blindly and start actually reasoning? How do we get it to explicitly explain its steps like a credentialed human expert? Researchers created a benchmark called GeoRC, or Geolocation Reasoning Chains. They collected 800 ground truth reasoning chains sourced directly from 3 champion-tier GeoGuessr experts, including the reigning world champion Raju Kasapo-Job. They are literally using the world champion's thought process as a grading rubric for artificial intelligence.
Using an LLM as a judge approach, they grade AI models against these expert human chains. They demand the AI identify fine-grained attributes and provide actual geographic support for its claims. The results? Even massive closed-source models like GPT-4 and Gemini still lag 12 points behind human experts at producing auditable reasoning chains. And smaller open-source models? They fail catastrophically, performing barely better than an AI guessing blindly without even seeing the image.
But there's definitely hope on the horizon. Researchers are now building new systems, like the SightSense 3-stage method, to mimic human thought. Instead of just guessing, the AI is forced into a sequence. First, it must explicitly detect fine-grained visual clues using object detection. Second, it uses those objects to retrieve external geographical knowledge. And finally, it fuses all of that information into a structured reasoning chain. It forces the machine to look at the world a bit more like we do.
What you should really take away from all this is that while AI can process millions of images and memorize textures we can't even perceive, true geographical reasoning, the ability to apply global context to a local clue, is still a uniquely human superpower. So I'll leave you with this thought. As models like SightSense get better at mimicking our logic, will AI eventually out-reason human intuition? Or will the chaotic, nuanced context of the real world always be too complex for a machine to truly see? Thanks for joining me on this explainer, and I'll catch you next time.